Yeah, hello everybody. It's 5 minutes past the hour, so it's time to resume our magic lectures. Last time we started with part 5, which brings us back to the space-time perspective, and where we now finally are able to construct the physical states of a string. So last time I already gave a brief outline how the procedure works. In short, we apply the conformal gauge. We construct a representation space for the canonical commutation relations. We then impose the constraints, which selects a subspace of physical states. And then we have to identify any states which differ by a residual gauge transformation. The residual gauge transformations are those not fixed by imposing the conformal gauge, namely conformal transformations. And then if everything works out correctly, we should get a proper Hilbert space, meaning that we have a positive definite scalar product on our space of states. I've already mentioned that this does not work in general, but it works if we fix the number of space-time dimensions to the slightly too high value of d equals 226. Last time, we already discussed the first step in the program, so we only need to briefly skip over the slides. We have our commutation relations. We have a ground state, which in the language of conformal field theory is the SO2C vacuum. We talked a bit about momentum eigenstates. It is convenient to work with momentum eigenstates despite that they are non-normalizable. When need be, one can always go to normalizable states, which are appropriate superpositions, which are square integrable, and which in quantum mechanics we would call momentum space wave packages. Then we have to also represent the oscillation states. For this, we have our creation and annihilation operators. And since we insisted on manifest Lorentz invariance, we can see that our scalar product is necessarily indefinite because we end up with a Minkowski tensor eta mu nu here, which is indefinite. But at this point, this is not a problem because the question is whether this space here is positive definite. So for the record, we have now a basis for our representation space of Fock space, which is momentum eigenstates with an arbitrary number of creation operators for oscillations being applied. So now we turn to the implementation of the constraints. Classically, the constraints are that the modes Lm and Lm tilde of the energy momentum tensor are 0. In the quantum theory, we impose this in the form that we say matrix elements of Lm between physical states should vanish. Given the hermiticity properties, we end up with Lm with M positive annihilating physical states. The operator L0 is a bit more tricky because it has an ordering ambiguity. Normal ordering, if we define it in the standard operator language of quantum field theory, means that we have to put all annihilation operators to the right of all creation operators. So for objects which appear in our operators Lm, this takes this form here, where I've given you the appropriate ordering. There's only an issue when one index M is positive and the other is negative, then we might need to reorder. Now, by inspection, if we look for Lms with M different from 0, then there is no ambiguity, because if you look at these operators, they only have an ambiguity if these operators do not commute with each other, but this only happens if M is equal to 0. Therefore, for the operators Lm with M different from 0, any ordering is normal ordering because everything commutes, and we don't have an issue. So I use CO and NO for classical normal ordering, and by default, we want operators to be normal ordered. But now we have a look at L0, and there we have an issue because alpha minus m and alpha n are a pair of creation annihilation operators, so then commute, the ordering matters. To get the normal ordered version, we start with the normal ordered expressions. We split it up into a negative part, or the part where n is negative, a part where n is 0, and a part where n is positive. And then applying normal ordering, we can combine the two sums, lose the factor 1/2, and the expression that we get in this way is for reference and given the name n, or the symbol n, and is called the number operator. So the normal ordered L0 is 1/8 of the momentum squared plus this number operator, which is normal ordered. Let's look now at the classical ordering. We do the same. We split up into negative sum over negative n's, positive n's, and 0 n's. But this time, the negative terms are in the wrong order. So if we just combine the two sums by relabeling n into minus n, we get this, with half of the terms not being normal ordered. Now, if we take the difference between classical and normal ordering, we can use the commutation relations, and we get, by the constant prefactor, we have the 1/2. We get, after using the commutation relations from taking the trace over eta mu nu, the number of dimensions d, and then we get a sum, infinite sum, over all positive integers. So this is, of course, divergent, and we see that the classical and normal ordering of L0 differ by formal infinite constant. Since L0, if we add in L0 tilde from the right moving sector as a worldsheet Hamiltonian, this is an ambiguity of the ground state energy of the string. In standard quantum field theory, in Minkowski spacetime, we can make our lives easy. We just impose normal ordering, and the ground state energy is 0, which is also the only Lorentz invariant value that we can have in Minkowski space due to Lorentz invariance. But this does not apply to us here, and it does not apply in general if you consider quantum field theory on a finite volume. And we are here on a finite volume on the worldsheet because the spatial extension of the string, and therefore the worldsheet, is finite. And whenever you are in such a situation, the ground state energy becomes a physical issue. In particular, the so-called Casimir effect that tells us if we do quantum field theory in a finite volume, then there's a volume dependence of the vacuum energy, which manifests itself in the form of measurable so-called Casimir forces. So how do we proceed? Well, one way to proceed for the time being is that we just parameterize the ambiguity that we are, and we say the constraint related to L0 is L0 minus A applied to phi equals to 0, where A is a constant, and we have a similar constant for the other sector. Now, it would be inconvenient to carry around this undetermined constant A, so I will already tell you now what the correct value is, namely the so-called no-Gauss theorem, which comes from unitarity, meaning requiring a positive definite scalar product, fixes A to be 1 together with D equals to 26. And I will, while we will discuss how this is shown later, we will already anticipate the correct answer and work with the correct value, so that this here are our physical state conditions. And what we will now do is analyze these conditions further. So, starting with L0, we already saw how this decomposes. The creation operators are eigenoperators for this number operator with eigenvalue m. And our basis is a basis of eigenstates. So what n, if we apply it, does, it essentially reads out these indices m1, m2, and so on from our creation operators. And the following, I will use the same symbol for the number operator and its eigenvalues, which I can do because I've chosen a basis of eigenstates. So there's no problem with doing this and simplifying my notation this way. So let's take the constraint L0 minus 1 on a physical state is equal to 0. We decompose L0 into momentum and number operator. Then we use that phi is an eigenstate. So we assume that we take a physical state which is an eigenstate of momentum and number operator. There's no restriction of generality because the basis with this property exists. And then the condition that we get is a relation between k squared and the eigenvalue of the number operator. But chi squared is minus m squared, so this is a formula which determines the mass, or gives us a constraint on the mass of our state. And if we, assuming that we are now working with a closed string, also add in the corresponding constraint with L0 tilde, we get a formula which tells us how m squared is related to n and n tilde. It's convenient to break these two equations up in the following form. One relation is a mass formula, which expresses the mass squared in terms of the oscillations n that we have put in. And the other condition is called level matching. And it tells us that, like in the classical theory, the left and right moving excitations contribute equally to the mass. And the only change that we have relative to the classical mass formula, which we had a few weeks ago, is this shift here of the ground state energy, which brings in this factor -2, which we will talk more about later. Since this is such an important formula, let's restore units and express everything in physical units. So far we used as the dimensionful constant in string theory, the string tension T, that was the coefficient in front of the action. The mass formula is conventionally expressed in terms of the so-called Registrar parameter alpha prime, which is up to a numerical factor 1 over T. So it is dimension length squared. And then the mass shell condition takes this form here. Right. And okay, here's for reference in string units. So our standard choice is T is 1 over pi, and alpha prime is 1/2. For reference, I also give you the formula for open strings. Here's a relation between alpha 0 and p has different numerical factors. So in L0, we have here 1/2 instead of 1/8. And then we have a slightly different Marshall condition. And of course, no level matching because we just have standing waves on the string. So as in the classical theory, the L0 constraints give us a mass formula and level matching with a little shift due to the Casimir effect of the ground state energy. We can now make a little list of mass eigenstates. This is here for the open string. In this table, we go here by level or occupation number. Here are the corresponding values of the mass squared. Here are the states. And here we give the corresponding representation of the Lorentz group, where I start to introducing Young tableau notation, which I will explain in more detail a bit later. The ground state is a scalar, and a scalar is here symbolized by a bullet. The first excited state is a Lorentz vector, for which we write a box, which stands for an index. And at level 2, we have a vector. And because alpha -1 mu commute, a symmetric tensor, and under the Lorentz group, a symmetric tensor is reducible and decomposes into a symmetric traceless tensor, and the trace, which is a scalar, and this is already anticipated here in the notation. But currently, we don't look at Lorentz representations at spin, but let's also talk a little bit about the masses. Due to the Casimir effect, we have a ground state which has a negative m squared, which we will now discuss in detail. Then the first excited state is 0 mass, and it's a vector, so this looks good. And then all the further states are massive, which is also okay. But what to make of this negative mass squared object? So the open string ground state has negative mass squared. Such states are called tachyons. Now, classically, these would be particles which propagate faster than the speed of light, but this is not the correct interpretation in quantum field theory. I've given here a wordy summary of what it means to find negative mass squared in the quantum field theory of a scalar, but it's better to explain using some drawings, which I will now turn to. So, as you can see here, mass in a scalar quantum field theory is read off from the shape of the potential. So if we have here, first I take a potential where I take here the value of the scalar field phi, and here the value of the potential energy. In the first example, I take something which has a minimum at phi equals to 0. And then how do we find the mass? Well, we expand the potential in a Taylor series around the minimum. So we have then the value at the minimum. Then we have the first term in the Taylor series, which is linear in phi. But if we are expanding around in extremum, this is 0. And then there is the second derivative term multiplied by phi squared. Now, if this is indeed a minimum, then this is second derivative at the minimum is positive, and this coefficient gives us the mass squared of the particle. But if the second derivative turns out to be negative, that means that we have a maximum of the potential of our theory, and that, as indicated in this drawing, tells us that we are not expanding around the correct ground state, but around a state in the theory which is not a stable state and therefore does not represent a stable particle. So if the theory has a true ground state or vacuum, then this potential should, of course, have a minimum elsewhere, and our job would then be to find this true vacuum, expand around it, and in this way find the spectrum of the theory. Yeah, here's an example of what you have to do if the potential of the minimum of the potential is not at the origin. So you find the critical value of the potential where the minimum is. You include a shifted scalar field where you subtract this so-called vacuum expectation value, and then you do your expansion. And again, now in this expansion, the linear term vanishes. And from the second derivative term, but now taken as a true minimum, you can read off the mass squared of the physical particle, which corresponds to excitations around the true ground state, phi equals phi star. Now, the way this works out in for the open string is the following. And this is one of the very few examples where one has been doing something with string field theory in order to prove what I sketch here. So this is a picture of the potential for this scalar degree of freedom of the open string theory. The point that we were trying to expand around here is this local maximum. And there is indeed a nearby minimum which has been found, which has exactly 0 potential energy. But what is this state? Well, it turns out that the true vacuum of the open string is the closed string. This can be expressed in the language of D-branes as follows. If we have Neumann boundary conditions in all 25 spatial directions, then we are in a state which corresponds to a D25 brane, which implements Neumann boundary conditions for all open strings. However, this D25 brane is unstable and decays. And once this D25 brane has decayed, there are no open strings left, just closed strings. And in this sense, the closed string vacuum is a true vacuum of the open string. To be precise, this refers to the bosonic strings that we have been studying so far. There's, of course, also then the question what happens if we construct string series containing space-time fermions, which are then supersymmetric versions of string series superstrings, which we won't be able to discuss in much detail in these lectures. I will make a few more comments on the way, but with regard to the open string vacuum, good, for the open string vacuum, this effect is understood. Unfortunately, that's not true with regard to the closed string vacuum. So it turns out that the closed string vacuum is also unstable, but in this case, at least for the bosonic string, but in this case, it's not known what it decays to. The attitude that we will be taking towards this is that we are treating the bosonic string as a toy example for supersymmetric strings. And for supersymmetric strings, the problem goes away because these have a different Casimir effect, which has the result that the ground state energy is in fact 0. So we will focus in the following on those aspects of bosonic strings which carry over to supersymmetric strings, which, as far as we know, are stable and don't suffer the tachyon problem. So let me then get back on track here. Where were we? Oops, sorry. Now again, yeah, there's a problem I had before. Let me try whether I get, yeah, that's a problem that I had once before when I switched applications. Last time I could solve this by closing this program here. So let me try whether this trick works out again. Okay, starting the program again. Here we are. I think I don't want to update. Okay, and now let's hope. Yeah, we are back in business. Very good. So let me scroll forward to where we left off, which is, okay, this were the summary of the tachyon state and how to think about it. So let's now focus on the first excited state, the massless state, which is a state that in a supersymmetric string theory you would find as the ground state. Good. So here we have some more work to do. So consider the most general level 1 state of the open string, which is this linear combination of creation operators alpha minus 1 with some coefficients zeta mu. The L0 constraints have told us that this is a massless state, but we now have to impose the further constraints, Lm, with m larger than 0. For the tachyon, it was clear that these further constraints don't impose conditions. But if you look at this state and the commutation relations between Lm and the alphas, then we find that for the level 1 state, the conditions with m larger than 1 hold automatically, but that we get a non-trivial condition if we apply L1. So we write this out. And then what you have to do is you have to substitute in what L1 is. It's an infinite sum in alpha, quadratic in alphas. You have to see whether there's any term which does not commute with alpha minus 1. And turns out there is a term involving alpha 0 and alpha 1, which does not commute with alpha minus 1. And then there's a usual trick that because alpha 1 will annihilate momentum eigenstates, you can replace the product by a commutator, use the commutation relations to apply, and then you get this condition out here. This condition tells us that states are physical if the vector zeta is Lorentz orthogonal to the momentum. And here we have then the full set of physical state conditions at level 1. The first is k squared equals to 0, the Marshall condition. And the second is the orthogonality between k and zeta. And I will refer to zeta as a polarization vector because we will see that it indeed has something to do with spin and polarization. Before getting there, we note the following. K is a null vector and therefore orthogonal to itself. And therefore, there are also physical level 1 states where the vector zeta is proportional to k, the momentum. These states are physical. But I claim these states with this particular choice of polarization are null states in the following sense. Firstly, if you compute the norm, then you find the norm is equal to 0, because if because the physical state condition is that k squared equals to 0, and they are moreover orthogonal to any physical level 1 state. Here I take the scalar product with a general level 1 physical state, which gives me this expression here. But in this case, either the two states are the same, in which case this is 0 by the physical state conditions that zeta and k are orthogonal, or they're a different state, but then they are killed by this momentum conservation function k prime different from k. I will realize that this argument is a bit sloppy, because the scalar product between k prime and k as momentum eigenstates is not a Kronecker symbol, but a delta function. So if you want to do this argument strictly, you should, this is one of the places where you should work with normalizable states, which I leave to you as an exercise, but I promise if you do this, you will find that my two statements here are okay. So you will see that the state psi has 0 norm. They are orthogonal to all physical level 1 states. And since states at different levels are always orthogonal, this follows that psi is orthogonal to any physical state itself. So adding these states psi exactly corresponds to making a gauge transformation, a transformation which does not change the physical state, but just gives us a different representative. And here's the summary, how these physical level 1 states are characterized. They're characterized by these 3 conditions. They are massless, they have transverse polarization, and polarization can be shifted proportional to the momentum. These are exactly the kinematical properties of a photon, but for those who not, or speaking more generally of a massless vector field, but for those who do not immediately recognize this, let us now explain why this is the case. And to do this, we go to a space-time picture where we start from the Maxwell equations, which we know to describe electromagnetic fields, and upon quantization, then photons. We formulate the Maxwell equations relativistically using the antisymmetric field strength tensor. And then the Maxwell equations, there are 2 Maxwell equations if we do it in this relativistic form. The first are the dynamical equations, which tell us that the divergence of F is given by the electromagnetic current. And then are the homogeneous Maxwell equations, which tell us that the curl or generalized curl of the field strengths are 0. The second set of Maxwell equations are not dynamical equations, but so-called Bianchi identities or integrability conditions, because they are the local existence condition for a vector potential A, so that we can write the field strength as a generalized curl of a vector potential. Now we can use this vector potential to describe the electromagnetic field, but the vector potential is a gauge geometry, because we can shift the vector potential by the gradient of a function without changing the field strength, which is the actual observable quantity. So this is an electromagnetism as a gauge theory formulated in position space. So in order to identify the particle content of a theory, one has to solve the free field equations, meaning the linear part of the field equations, because then one gets to particles by quantizing, by imposing canonical commutation relations. So we set the electromagnetic current equals to 0, so that we have the free Maxwell equations, which we have to solve. The homogeneous equations we solve by introducing the vector potential and expressing then the inhomogeneous equations in terms of A gives us this here, The first term contains the wave operator. Then we also have a second term, but now we can use gauge invariance in the following way. We can impose the so-called Lorentz gauge from Professor Lorentz without a t, which is that the divergence of A is equal to 0. And then the second term is away, and our field equation just becomes the wave equation for A mu. And this gauge is Lorentz covariant, as we observe, and this is now Professor Lorentz with a t, because, well, it is written in relativistically covariant form. So that's something we can do without giving up manifest Lorentz invariance. If we have done this, we still have a residual gauge symmetry, and we can still shift the vector potential A by a gradient of a function which obeys the wave equation. So it's not a complete gauge fixing. General states can be expressed as superpositions of plane waves, or if you like, they can be expanded in terms of momentum eigenstates. This is just the Fourier integral, where we have our plane waves e to the ikx, or if you want momentum eigenstates, there is some amplitude in front. This is a polarization vector, which in this integral then is a function of k. And then since A is real, I have to add the complex conjugate, but I didn't write it. There's a standard translation from position to momentum space, and we see the wave equation becomes the mass shell condition, k squared equals to 0. The Lorentz gauge becomes the transversality between polarization and momentum, and the residual gauge symmetry becomes the freedom to shift polarization parallel to the momentum vector. And here we see that these are precisely the conditions that we got by imposing our Virasoro physical state conditions on our level 1 state. You can get an explicit decomposition of either A or zeta into 3 types of modes. There are the unphysical components, which are projected out by physical state conditions. There are the actual physical degrees of freedom, and then there are spurious or pure gauge degrees of freedom. But to obtain this decomposition explicitly, we have to make an explicit choice of the momentum vector. So if we take this to be this here, which is a plane wave, or if you prefer a photon propagating along a particular axis, then this uses up part of our Lorentz symmetry, but we still have a residual Lorentz symmetry because we can still make rotations on this inner part of the vector where the coefficients are 0, and this group SOD-2 we will refer to as the transverse rotation subgroup of the Lorentz group. Having made a choice for k, we cannot work out what the physical polarization vectors are, and the constraint of transversality gives us this form for the polarization vector, where the first and the last entry are related. And now we can split this into a purely transverse part, and this we can take as a representative of the true physical degrees of freedom, and a spurious or pure gauge part, which is a part proportional to the momentum vector. We can make now a complete gauge fixing. For example, we could choose alpha equals to 0, then the transverse part would represent our physical degrees of freedom. Such a complete gauge fixing always breaks manifest Lorentz covariance. If we go back to position space, we can make such a complete gauge fixing by imposing the Coulomb gauge on top of the Lorentz gauge. This is a non-covariant gauge, so to write it, we split up our Lorentz vectors into a scalar and into a vector with respect to rotations. Then first line is the Lorentz gauge, and now we impose on top the Coulomb gauge, which is it's a spatial divergence of A is equal to 0, or translated into momentum space, the wave vector and the spatial part of the polarization vector are orthogonal. Yeah, for a plane wave in our preferred direction, this looks like this. And you see this precisely corresponds to alpha equals to 0 on the previous slide. In 4 dimensions, there's some further simplification. The Lorentz group SO1 is SO13, and the group which is left over after gauge fixing is the 2-dimensional rotation group SO2, which acts on the 2 transversal polarization degrees of freedom. This is written here in this formula, rotation matrix acting on the two linear polarization components. And then one can, and this is usually done in optics, take complex linear combination, shows the so-called circular polarization basis, which is given here. And then the rotation matrix is diagonalized. And from this form, we can read off the so-called helicity associated with the two states. Left and right circular polarization corresponds to a helicity plus or minus 1. Helicity is always the power with which e to the I phi appears as the eigen value when you perform this rotation. Mathematically, of course, what underlies this is the isomorphism between the rotation group SO2 and the group of phase transitions U1. Okay, so photon is a particle where the physical states have helicities plus and minus 1. Let's formulate this a bit more generally. So in quantum field theory, one-particle states are classified by their mass and their spin. More precisely, the mass can either be positive or zero. And for massless particles, the relevant quantity is called the helicity. Group theoretically, what the spin corresponds to is a representation of the rotation subgroup of the Lorentz group, whereas helicity corresponds to a representation of the helicity or transverse rotation subgroup of the Lorentz group. And what these two numbers characterize, mass and spin or helicity, are unitary irreducible representations of the Poincare group. And this is how group theoretically one can characterize one-particle states in a quantum field theory. They are, we look at the Hilbert space, we find what are the unitary irreducible representations of the Poincare group on it, and these tell us what the one-particle states in a quantum field theory are. To expand a little bit on this, for massive particles, so suppose in the first step we have to just find out whether the particle which we discuss is massive or massless, assume that it's massive, then we can use Lorentz transformation to bring its momentum to a standard form. And for a massive particle, this would be the rest frame, which takes this form, where only the first entry corresponding to energy is populated. And then we see, since all the other entries are zero, the leftover of the Lorentz group is the full rotation subgroup of the Lorentz group. And then what the representations here due to Wigner tells us, once we have fixed the mass, what we are still allowed to do in order to fix a representation of the Poincare group is we can choose any representation of the full rotation subgroup. For massless particles, the story is a bit different, because the standard representative is different and the leftover group from the full Lorentz group is a bit smaller. This leftover group is called the little group, and for massless particles, it is effectively this transverse rotation group SOD-2. Actually, the proper mass is a bit more complicated. It turns out the technique is a little group, or leftover of the Lorentz group after imposing the standard form, is a bit larger. It is a D-2 dimensional Euclidean group, which is again like the Poincare group, which is not semi-simple. And then one has to iterate this construction and find the little group of the little group. And this then turns out to be SOD-2. Since it's a bit silly to say little group of the little group, I will refer to this as a little group. Anyway. Now, let's add some further observations on this. In field theory, we have seen specifying the free or linear part of the field equation does nothing more and nothing less than specifying the mass and spin helicity of the corresponding particles, and thus group theoretically specifying the linear part of the field equation means specifying irreducible representations of the Poincare group. Of course, one must be careful to expand around a true ground state, as we discussed in the tachyon example. And a related example would be if the theory has a Higgs mechanism, then in order to see the particle spectrum correctly, we have to expand around the true minimum. Now, from our string theory worksheet perspective, the Virasoro constraints, as we have seen, also determine mass and spin helicity. Just so it means that they identify representations of the Poincare group, and therefore the free part of the field equations of these string states is determined once we know the Virasoro constraints. In other words, we can read off the free part of an effective field theory for the given state. So, for example, for our photon-like state, the free part of the effective field theory is the Maxwell action. Good. We have 10 minutes left, so I think I can continue and explain to you what we need to know about group theoretical techniques to understand what spin and helicity various string states have. I will use the Young tableau technique. I will not have the time to explain this fully, but I will give you all the information that you need to work within this course. So, how does the notation work? For every vector index or fundamental representation of the groups, and for us the relevant groups are the rotation group or Lorentz-like groups. Anyway, vector indices are represented by a box, scalars by a bullet, and then we use vertical arrangements to indicate antisymmetrization and horizontal arrangements to indicate symmetrization. And then, and there's a difference between Young tableaus for SU, unitary type groups, and SO, orthogonal type groups. For orthogonal type groups, the trace of a symmetric tensor is by itself a representation. It is invariant under Lorentz transformations or rotations, and therefore the irreducible representations are not symmetric tensors, but symmetric traceless tensors. So for us, the horizontal arrangement of boxes means a symmetric traceless tensor. Dimensions of some irreducible representations are given here. Simple counting, scalar is one-dimensional, vector is n-dimensional, just the different values that the index can take. Antisymmetric tensors is antisymmetric combinations of two objects which can take n values, so it's 1/2 n minus n times n minus 1. And then symmetric traceless, symmetric arrangements would be 1/2 n times n plus 1, but we have to take out the trace, so this gives a -1. For the closed string, we will need to know how to multiply representations. Specifically, we will need to know what happens if we multiply the vector representation with itself. This gives us symmetric traceless tensor, an antisymmetric tensor, and the trace. And the first step, that there's a symmetric and antisymmetric piece that is easy to check, that if you have a Lorentz tensor depending, or rotation tensor depending on two indices, that symmetric and antisymmetric part don't mix. But the extra thing for the SO groups is that the trace is a scalar, it's a representation in its own right, so we have to take it out. That would be different for SU type groups, that we don't have this invariant, the trace. What we also need in order to get from the Lorentz group to the little group are so-called branching rules. These are decomposition rules for decomposing representations of a group with respect to a subgroup. And we go from either the rotation group or a Lorentz group to a rotation subgroup. Well, scalar remains scalar, it's clear. A vector decomposes into a vector plus a scalar. Again, for dimensional reasons, this is clear. Antisymmetric tensor goes to antisymmetric tensor plus a vector. Again, you can check this by just investigating what the dimensions of these representations are. And a traceless symmetric tensor goes to a traceless symmetric tensor plus a vector plus a scalar. So again, by looking at the counting, you discover that once you decompose a symmetric traceless tensor into a symmetric part, into a second rank tensor and into a vector, that the symmetric part again needs to be made traceless in order to have irreducible representations. So this is all pretty much uniquely fixed by the dimensions of the representations, and these are the rules that we will need in order to understand the open and closed string spectrum. Now, let's return to the photon state and give it a group theoretical representation. These were our conditions here. It's originally given in terms of an oscillator, which is a Lorentz vector. It's massless, so the little group is the transverse rotation group. So we apply the branching rules twice, and we obtain a vector and two scalars, and this fits with our decomposition into d minus 2 physical degrees of freedom, 1 gauge degree of freedom, or spurious degree of freedom, and 1 unphysical degree of freedom. In 4 dimensions, the little group is actually abelian. Abelian groups have only one-dimensional irreducible representations. So what happens to the Lorentz vector is it decomposes into 4 scalars of helicity 1, -1, 0, and 0 respectively. And the helicity plus minus 1 are the physical ones, and the helicity 0 ones are the gauge and the unphysical one. Good. Now let's turn to the similar analysis for the closed string. Here I've made a table, including, we also have to respect level matching. So everything is still labeled by the level. Here's the mass spectrum. So we start again with a tachyon, which is a scalar. And I already discussed it is not really known what the true ground state is. But if we would do a supersymmetric series, then this state would not be there, and the spectrum would start from here, and would in fact have precisely a state with the same structure than we have in the bosonic string. So we will focus on this mass 0 state. This is a general second rank tensor. And then we see if we go to massive states, we have quite a few different combinations with tensors of various ranks. But let's focus for the rest of this lecture on the second rank tensor. Okay, this is one remark about the closed string tachyon, which I've already given. So let's now go to the massless closed string states. A general combination contains the polarization tensor theta mu nu. This is a generic second rank tensor. The only constraints which impose additional conditions in addition to level matching and the mass formula are the L1 constraints. If we work them out, it tells us that contractions of the polarization tensor with the momentum vector must be 0. Now to proceed, we decompose the polarization tensor into symmetric and antisymmetric part, which then need to have the property that when we contract them with momentum, we get 0. Let's look at the symmetric part. Here it is. These are the conditions that we have. And now, like for the photon-like state, we have null states. And these physical null states correspond to symmetric bivectors, which are formed out of the momentum and an auxiliary vector zeta, which must be Lorentz orthogonal to the momentum. So here are the residual gauge transformations. We can shift our symmetric tensor by the symmetric bivector, which is itself subject to this constraint. Now, since we deal with the Lorentz group, the trace of the symmetric tensor is by itself a Lorentz scalar. And therefore, what we now do is we decompose S mu further into a traceless part and a trace part. To do such a decomposition explicitly, we pick a light-like vector, which has a prescribed scalar product with the other light-like vector, the momentum. With this auxiliary vector, we can then explicitly write down a traceless part and a pure trace part of S, given by the formulas quoted here. And to verify them, you observe that psi and phi add up to S. Psi is indeed traceless, and trace of phi is the same as trace of S. So this is then my successful decomposition. The trace part of S mu nu is a physical state, and it's not a null state. It's in particular invariant under the residual gauge transformation, and that means that this trace part is a physical state, which is a scalar, and the scalar is called the dilaton. We will discuss later that the scalar field has a property that its vacuum expectation value is not determined, at least at tree level, therefore is a free parameter, which is related to the value of a dimensionless string coupling constant that we can introduce. Now to the traceless part, which needs to be transversal. we can parameterize this explicitly by making a choice for our momentum vector. Now my alert reminds me that our time is up. So I should stop here, but to whet your appetites for next time, what we will discover with regard to the state is one of the most exciting things about string theory, namely that this state can be interpreted as a graviton in the same sense as we could interpret the massless level 1 state of the open string as a photon. But I think this will have to wait for next time. So thank you for joining. Today I will stop the share now, I think. Oops. Okay, here we are. And as usual, I'll hang around in case anybody has a question. Otherwise, looking forward to seeing you next time. Bye-bye.